Greetings for everyone. This is Siddharth, Department of Civil Engineering, Hindustan College of Engineering and Technology. Today we will be seeing about the topic RC beams. In this slide we will discuss about the basic steps to design a RC beam. So first and foremost we have to assume the section size, grade of steel and concrete according to the structure to be built. That is, every detail can be taken from IS 456, like every steps to be followed is given in IS 456. So first we have to assume the size and grade of steel and concrete. Generally for grade of steel Fe 415 is used, and for concrete it ranges from M20 to M40 or M50, based on the loading conditions. After which we have to calculate the total UDL, that is what is the total load that is acting on our structure. From this only we can get the factor load, like if you calculate all the loads that are acting at a particular building, say UDL, point load, other load, wind load, seismic load, live load, everything to be added, you will get one value, and that has to be multiplied with 1.5, which is the factor of safety for concrete, so that you will get the factor load. From this factor load you have to calculate the factored moment. So this factored moment will give you the certain ideas about the load, that is our moment and shear force acting on your building. So for this we have to revise the size. So there are formulas given in IS 456 for this to calculate the depth required according to the moment acting on the structure. So for using this we can resize the structure and grade of materials if it is required. If the depth provided is not required, we can increase it. If the grade of the material provided is not enough, we can increase it. Then from this we have to calculate the AST required, that is area of steel required for our beam. So we have to calculate this, and according to this AST value we have to provide the reinforcement, like 10 mm of rods at a distance of spacing 300 mm or 250 mm. We have to give these details. If you are going to list out or able to understand all these things, we can further go into our next PPT, where we will be explaining in detail about the steps to be followed for design of RC beam. So here in this PPT we will see about the beam, basic ideas about beam only. So beam is a horizontal structure member used to carry vertical load, shear load and sometimes horizontal load. This is an exact definition for a beam. So first of all, beam is a horizontal structure. It is not a vertical one, and it is used to carry vertical load from the above structures, or shear load and sometimes horizontal load too. Here horizontal load is nothing but your wind load and seismic load. There are many types of beams. Okay, we are going to see about an RCC beam, singly reinforced beam and doubly reinforced beam. Here if the beam is a singly reinforced beam, the condition has to be satisfied, like if the factored moment mu is less than the limiting moment, then the beam is designed as a singly reinforced beam. We mostly use the singly reinforced beam in the building if the stresses are very low. Practically this is being eliminated right now. We are not going for any singly reinforced beam, because this idea gives an the reinforcement only at the bottom part, which is not very good in the practical cases. So if your stresses are too low, or if you are going for load bearing structures, the singly reinforced beams can be used. The bottom reinforcement are designed to resist the tensile load. So for tensile load, bottom reinforcement are given, and for the top compression load, no reinforcement are given. So okay, so top reinforcements are also provided in the singly reinforcement beam, but it is designed to hold the stirrups in position and not designed to be carry the compression load. This is a most important point. Here we have already discussed that for a singly reinforced beam we are not providing any bars on the compression part, that is on the top part, but to hold the bottom reinforcement in position we are going to give some top reinforcement. So for this top and bottom reinforcement to be in place, we are going to design one stirrup. So this stirrup is going to hold the top and bottom reinforcement, and main thing is that the top reinforcement are not designed to carry the compression load. This is the most important part. This is for your doubly reinforced beam. When the factored moment mu is greater than the limiting moment, then the beam is designed as a doubly reinforced beam, where mu is greater than mu limit. The bottom reinforcement are designed to resist the tensile load, and top reinforcement are designed to resist the compressive load. This is the most important part and most commonly used beams in all RC structures. Even though we are calling a singly reinforcement beam, even if there are reinforcement at the top and bottom part, and also for doubly reinforced beam we are talking about reinforcement at the top and bottom part again. So practically thinking there is no kind of difference there, but the main difference is that this top reinforcement is also designed to resist the compressive load. This is what actually differentiates your singly reinforced and doubly reinforced beam here. The doubly reinforced beam is more suitable where there is a higher chance of earthquake or stress reversal, also if an increase in depth is limited for the beam. So this is the most commonly used beam here, and we are using this beam we can safeguard our buildings from earthquake, because this will be able to take more loads, like later loads can be taken very well by this doubly reinforced beam, or if the stress reversal is happening due to this continuous loading, this can be used. Also if the depth increase is limited, if you are not able to increase the depth of your beam, then you can go for your doubly reinforced beams. Here we will be talking about beam sections. We have three beam sections in general. The first one is balance section, where the balance section is clearly defined by this area, like the strain in concrete and steel will reach their limiting value simultaneously. For example, if you are talking about loading conditions, if you are giving maximum load, ultimate load to a building, then the strain in concrete and stress will reach simultaneously, meaning that strain in concrete and steel, like the failure pattern in concrete and steel, or at which point the steel and concrete fails, will be a very simultaneous one, and this is not generally preferred for buildings, because concrete is generally fails by concrete generally fails by brittle mode, and steel generally fails by ductile mode. It is very safe to have failure in steel first rather than concrete, where concrete is a brittle failure, like a glass material will fail. But as far as steel is concerned, it is a ductile material, so we will have some time. So this balance section is almost to be neglected, but at certain cases we are using this. And the second one is under reinforced section, where the steel will fail first, with showing the warning if under reinforced section is used in the beam. This failure is called ductile failure. Every designer prefers to design the section according to under reinforced section. Like if you are able to calculate the area of steel that is required for a beam, right, and there is area of concrete required for a building, concrete for a beam, you are going to provide concrete, that is enough concrete is provided for the beam. But if you are, for example, if you are talking about one beam, then that 1000 mm square is the AST required, but I am going to give only 900 mm square, so there is a 100 mm square lagging there. That is 100 mm square of steel is not provided, where 1000 is required. So at this point of time, when the ultimate load comes first, steel, the material is not provided in enough manner, so it will fail first. We have already discussed that the steel fails only by ductile method. So the brittle failure of concrete is totally neglected. Brittle failure requires very less period of time, and for ductile failure it requires more period of time. So using this period, we can actually get out of the building. Like there will be some warning signs, and the deflection may be more, or some cover part may be failing, or some part of concrete may be it may be breaking. So there will be certain signs for our visual parameter, so we can sense that and we can go out of the building. So that is the main part of our under reinforced section, where we will be able to escape from the building if there is one problem or if there is a failure. Similarly, there is a over reinforced section, where the concrete is given as far as the enough section, right, if the required number of required amount of concrete is provided. But as far as concrete steel is concerned, if 1000 mm square is required, I will be providing 1200 mm square. So this means that steel is already given on a more manner than the required one. But as far as concrete is concerned, it is also given as per the limit. So if the ultimate load is happening, there is a 200 mm square extra in the steel part, which will safeguard it in the steel failure alone. But concrete, as far as is concerned, 1000 mm square is required, so 1000 mm square is given. So if there is a failure, it will suddenly fail. It will fail first before your steel. So this sudden failure is a brittle failure, and this should be avoided as far as possible. If brittle failure is happening in buildings, it is not a very good sign, and this may lead to loss of life and property. So this one reinforced sections is not generally provided for any sections. It is not preferred, and balance is also not preferred. We have to go for under reinforced sections alone. In the coming PPTs, we will see about the design of beam members according to our IS 456-2000 in a very detailed manner. Thank you.